Chapter 1. The submarine that can't stop, the needle is almost at zero. You are 200 meters underwater, 2,000 kilometers from any friendly port, and stopping is not an option. On a surface ship, running out of fuel means you drift. On a submarine, it means something far worse. Picture the central control room, dim red lighting, the hum of ventilation you stopped noticing 3 weeks ago. An officer leans toward the commander and says 4 words nobody wants to hear on a deep patrol. Fuel reserves critically low. The diesels that power this machine, the same ones that charge the massive battery banks the submarine glides on in silence, are starving. And here's the thing most people don't understand about a diesel-electric submarine running low on fuel. It doesn't become lighter. It doesn't start to float upward. It holds its depth perfectly, suspended in the cold dark like nothing is wrong at all. That seems impossible. An empty tank weighs less. Any ship losing mass should rise. But this submarine has been engineered at a level of precision that makes the obvious answer wrong. The fuel system doesn't work the way any driver on the surface would expect. And the reason it works the way it does comes down to a pressure problem so severe that if engineers hadn't solved it, the tanks themselves would simply be crushed flat by the ocean the moment any fuel was burned. At depth, the water pressure outside the hull is measured in hundreds of atmospheres. A sealed, empty metal tank at that pressure doesn't stay sealed and empty. It collapses inward instantly, like an aluminum can under a truck tire. That single physical fact forced submarine engineers to make a decision that sounds completely insane the first time you hear it. They opened the fuel tanks to the sea. But how they did it, and why the fuel doesn't just pour out into the ocean, is where the engineering becomes genuinely brilliant. That explanation is coming. But first, understand what it costs to run out of fuel out here. The batteries can power the submarine in silence for days. The electric motors are quiet enough that enemy sonar struggles to find her. But batteries have a hard limit. When they drain, the sub must rise toward the surface, raise a thin steel pipe called a snorkel above the waves, and run the diesels. For up to 8 hours at a time, in the dark, hoping no one is watching. And that snorkel, that slender mass cutting through the water, leaves something behind. A white foam trail visible from aircraft. Diesel exhaust detectable by chemical sensors. A radar cross-section that modern anti-submarine aircraft are specifically trained to hunt. Every time the snorkel goes up, the submarine becomes slightly less invisible, and now the fuel is almost gone. The only solution left requires the submarine to do the most dangerous thing it has done in months. It has to surface. Chapter 2. The insane engineering trick that keeps it hidden, deliberately flooding a fuel tank with seawater, is the kind of thing that would get a car mechanic fired on the spot. On a submarine, it's the reason the whole machine works. Here's the problem engineers faced. Diesel fuel must be stored somewhere inside or around the submarine's hull. As the engines burn that fuel, the tank empties. On land, an empty tank fills with air. No problem. But underwater, an air pocket inside a metal tank is a structural catastrophe waiting to happen. The pressure outside at 200 meters is roughly 21 times the pressure at the surface. That asymmetry, full ocean pressure on the outside, near zero on the inside, will buckle and destroy any sealed, empty tank. So the tanks cannot be allowed to become empty voids. Something must fill them as the fuel burns. The solution is elegant and unsettling in equal measure. Engineers placed the main fuel tanks outside the pressure hull, in the space between the inner and outer hull of the submarine, and they punched holes straight through the bottom of those tanks, connecting them permanently to the ocean. Seawater can flow freely in and out. The pressure inside always matches the pressure outside. The tanks can never be crushed because they are never truly sealed from the sea. Now the obvious question, why doesn't the fuel just dissolve into the ocean? The answer comes from a phenomenon anyone who has made salad dressing has witnessed. Pour olive oil into a glass of water. No matter how hard you shake it, the oil floats back to the top. Every time. Diesel fuel behaves exactly the same way. It is significantly less dense than seawater, so it rises. It always occupies the upper portion of the tank. Seawater fills the bottom. As the engines consume fuel from the highest intake point in the tank, the fuel level drops, and seawater rises from below to take its place, acting as a slow, precise, natural piston, pushing the remaining fuel upward toward the engine. The submarine's weight stays almost perfectly constant throughout the patrol. Seawater replaces diesel gram for gram. But the system has one dangerous flaw. At the boundary layer where diesel and salt water meet, a chemical reaction slowly produces a layer of emulsified sludge, a thick, dark contamination that is neither fuel nor water. If that sludge reaches the engine, it causes immediate breakdown. So every drop of fuel passes through a centrifuge separator before it enters the engine, a machine that spins at extreme speed, using the difference in density to fling contaminants outward and deliver clean fuel to the center intake. The system works, but it requires constant vigilance, and it requires the crew to eventually do the one thing the entire patrol has been designed to avoid. Chapter 3. 4 hours that could end everything. There is a 4-hour window during every diesel submarine patrol when the entire mission, months of silent work, thousands of kilometers traveled, every precaution taken can be destroyed by a single satellite passing overhead. Open ocean refueling between a submarine and a tanker sounds plausible until you think about the details for 30 seconds. 2 massive steel hulls, side by side, in a 5-meter swell. Heavy fuel hoses under pump pressure, each one fighting every movement of the ships like a fire hose connected between 2 buildings swaying in an earthquake. A single collision between those hulls, and on rough seas, collisions are not a risk, they are a certainty, can rupture a hose, spill hundreds of tons of diesel, and leave both vessels dead in the water. Worse, from low Earth orbit, 2 ships sitting motionless in the open ocean emit heat signatures, radar reflections, and visible wakes that intelligent satellites are specifically programmed to notice and flag. A stationary pair in the middle of nowhere is exactly the anomaly analysts look for. So the real refueling of a diesel submarine happens somewhere it cannot be seen. A deep fjord on a coastline with no civilian traffic. A bay behind an uninhabited island. A hidden inlet that doesn't appear on commercial shipping charts. The submarine arrives at night, running on battery power, no lights, snorkel lowered. A supply vessel, deliberately unremarkable, a ship that looks like a coastal freighter carrying anything at all, has been waiting. It moves alongside without a word on radio. The work that follows is brutal and physical. Fuel hoses on a submarine supply operation are not lightweight connections. They are thick, heavy-walled pipes, pressurized to dozens of atmospheres, and they move. As fuel pumps through them, they vibrate and whip and strain against their couplings. The sailors handling them on the submarine's slick outer deck work in darkness, in whatever sea conditions exist, with the hull beneath them rolling and the hoses trying to tear out of their hands. The transfer of hundreds of tons of fuel takes hours, and throughout every minute of it, the submarine is defenseless. It cannot dive with hoses connected. It cannot accelerate away. It sits on the surface, large and slow and completely visible to anyone looking in the right direction, which is exactly why, built into every fuel coupling on a submarine supply system, there are emergency disconnect valves. If a threat is detected, a radar contact, an aircraft, a signal intercept, there is no time to uncouple cleanly. The valves fire. Both ends of the hose snap shut simultaneously, preventing spill. The hoses fall away. The hatches seal. From the moment the order is given, a modern diesel submarine can be under the surface in under 2 minutes. The supply vessel turns and runs its own course. There is no debris, no communication, no evidence anything was there at all. That is the reality of keeping a diesel submarine fueled. It is not a logistics operation. It is a disappearing act performed under time pressure in darkness with no margin for error. And it is the reason that, starting in the 1950s, the engineers and admirals who understood what submarines could do began working obsessively on a way to never need it again. Chapter 4. The reactor that made the problem disappear. 1 kilogram of highly enriched uranium contains the energy equivalent of roughly 3 million kilograms of diesel fuel. That single ratio changed everything that came after it. When the USS Nautilus sailed under the North Pole in 1958, the first submarine in history to do so, it did it on nuclear power, traveling 2,000 kilometers under Arctic ice without surfacing once. No snorkel, no tanker, no vulnerable window on the surface. The diesel-electric submarine, which had dominated naval warfare for 50 years, was made obsolete in a single voyage. The physics inside a nuclear submarine reactor are straightforward to describe and staggering to contemplate. Uranium atoms split. That splitting releases heat, enormous, continuous, sustained heat from a fuel source so dense that the entire reactor core, the piece that powers a 10,000-ton warship for decades, is roughly the size of a large trash can. That heat is transferred to water in a closed primary loop, which heats a secondary loop, which produces steam. The steam spins turbines. The turbines turn the propeller shaft and drive generators. The generators produce electricity in quantities that no diesel system could approach, and that electricity is the revolution. Not just propulsion, everything. The submarine's desalination plants take raw seawater and produce fresh water continuously, enough for cooking, showers, laundry, and the ship's systems, with no external supply. The oxygen generation systems, electrolysis units that pass electrical current through purified water and split its molecules into hydrogen and breathable oxygen, run around the clock without any stored air supply. The crew breathes manufactured oxygen for months. Note that the seawater cannot be electrolyzed directly. Saltwater electrolysis produces chlorine gas, which is lethal. The water must first be desalinated, then electrolyzed. The hydrogen produced in the process must be carefully managed. Released directly into the ocean, hydrogen bubbles create an acoustic signature detectable by enemy hydrophones at significant range. Modern systems neutralize the hydrogen chemically rather than venting it. The result is a machine that is, for practical purposes, self-sustaining. The Virginia-class attack submarine has a reactor core designed to last its entire 33-year service life without ever being opened. The Columbia-class ballistic missile submarine carries a reactor designed for 42 years of operation. These vessels are built at the shipyard, the reactor is installed, and that reactor runs continuously until the submarine is decommissioned. No refueling, no fuel logistics, no vulnerable window on the surface waiting for a tanker. The only thing that brings a nuclear submarine home is the same thing that grounded every explorer in history. The food runs out. Crews carry approximately 90 days of provisions. When the last ration is accounted for, the mission ends. Not because the power failed or the fuel ran low, but because the men are hungry. The ocean, it turns out, is still limited by the stomach. Chapter 5. The blue glow that shouldn't exist. In a room-sized pool of water somewhere inside a radiation-shielded facility, the spent fuel rods from a nuclear submarine reactor glow vivid, impossible blue, not from heat, not from chemistry, not from a physical phenomenon that requires particles to travel faster than light. Let that settle for a moment. Nothing travels faster than light. That is not a law that gets exceptions. And yet the glow is real. It is measurable. It was first documented by Soviet physicist Pavel Cherenkov in 1934, and it earned him the Nobel Prize 24 years later. The resolution to the apparent contradiction is this: nothing travels faster than light in a vacuum, but light does not always travel at its vacuum speed. In water, light slows by approximately 25%. The charged particles streaming out of spent uranium fuel, moving at velocities set by nuclear physics, not by the medium they're traveling through, do not slow down proportionally. They keep moving at nearly their original speed. In water, that speed exceeds the local speed of light. The result is a shock wave of photons, the optical equivalent of a sonic boom that radiates as an eerie, brilliant blue. Anyone who has watched it describes it as the most otherworldly thing they have ever seen. The process that produces this light begins with the submarine entering dry dock. The entire vessel is pulled from the water and placed on supports inside a specialized facility, one designed to handle highly radioactive material at every stage of the operation. The reactor is shut down. Even after shutdown, a nuclear reactor continues generating decay heat for days and significant residual radioactivity for far longer. It must be cooled, monitored, and isolated before any human approach is possible. Every component between the outer hull and the reactor core is logged, cataloged, and removed. The USS Louisiana, the last Ohio-class submarine to undergo this process, completed its refueling and overhaul in March 2023. The work took 40 months and consumed 870,000 person-days of labor. The cost of a nuclear submarine refueling runs between $600 million and $800 million. That number is why the Navy ultimately decided to design its way out of the problem. When the spent fuel rods are finally extracted, lifted by precisely calibrated cranes from the reactor shaft and lowered into the water storage pool, the Cherenkov glow appears. The crane operators performing this work are not working in the dark. They are working under radiation safety protocols in lead-shielded facilities, monitored continuously, and they are working with tolerances measured in millimeters. The reactor shaft that holds the fuel rods is engineered to exact dimensions. A spent rod that tilts even slightly during extraction can bind in the channel. A bound rod cannot be safely removed without risking a disruption of the thermal management of the system, potentially a serious failure in a facility handling the most radioactive material on the planet. Every movement of the crane is verified against instrumentation before it is made. Fresh fuel cassettes are installed with the same precision in reverse. The reactor compartment is sealed and welded shut. The system is pressurized and tested at every stage. Then comes the moment that determines whether months of work held. The first restart. Control rods are withdrawn incrementally. Instrumentation watches for the specific signature of a sustained chain reaction, not a runaway, not a subcritical fizzle, but the precise, self-sustaining nuclear fire that the entire machine was designed around. When the readings confirm it, the turbines begin to turn. That low, continuous hum means the reactor works. The dry dock floods. The submarine rises off its supports. It moves under its own power for the first time in over 3 years, and somewhere ahead of it is another 2 decades of ocean, with no tanker meetings, no vulnerable windows, no foam trail on the surface. Just depth and silence and the quiet work of a machine powered by physics that still makes the people who understand it stop and stare at a blue glow in the dark.